Hello, greetings, welcome. So this is our first set of lecture notes from Chapter 1 on the scope and language of thermodynamics. So as a note, right, so I'm assuming that you're reading the book, right? There's a reading quiz based on you reading the book. So in these lecture notes, right, in Chapter 1 and all subsequent chapters, I don't hope to cover everything you could possibly need to know from that chapter. Right. So all I want to try and do is have some general discussion about some of the highlights and important concepts from the chapter. Okay. So in chapter 1, we'll have two sets of notes. I'll try and break up the other chapters into smaller, digestible parts. But again, I'm assuming that you're reading the textbook in detail. And so here I'm just trying to offer some general conversation and highlight some important parts or concepts from the chapter. Okay. But I won't cover everything. So here we go. All right. So I want to start up with a quote from Albert Einstein. All right. So thermodynamics, right, is it the greatest subject ever? Right. And so Einstein quoted, "A theory is the more impressive, the greater the simplicity of its premise, the more different kinds of things it relates, and the more extended its area of applicability. Therefore, the deep impression the classical thermodynamics made upon me. It is the only physical theory of universal content which I am convinced will never be overthrown within the framework of applicability of its basic concepts." So I personally feel that thermodynamics is a pretty amazing subject. Right? So the field of thermodynamics originated in the Industrial Revolution. Right? We'll talk about this in a moment. All right, so in this class, we'll learn about the first law of thermodynamics. So the first law of thermodynamics was interested in converting heat to work, right? The whole premise of the steam engine, right? So first law of thermodynamics originates based on, the need or desire to convert heat to work. Second law of thermodynamics essentially results from trying to understand the, maximum efficiency of these processes. Okay, so thermodynamics originated during the Industrial Revolution, where people were trying to convert heat to work. Okay. Since the Industrial Revolution, so molecular theories have evolved, right? The field of science has evolved. But those foundational laws laid down during the Industrial Revolution still hold and have yet to be overthrown. If anything, the range of applicability of the first and second law have expanded greatly. Okay. In contrast, think about, your Newtonian physics course that you took during your, say, first or second year. Right? So Newtonian mechanics, in theory, was shown to have limitations by Albert Einstein in his theory of relativity. Right? But thermodynamics is still holding strong, and if anything, its range of applicability has just evolved. And the advent of molecular thermodynamics, molecular theory, and modern day physical theories have only further confirmed the classical laws of thermodynamics. Right, so it's a pretty amazing subject. So the origin of thermodynamics, right? So thermodynamics is essentially, our engineering thermodynamics that we're interested in this course is essentially going to involve the relationship between heat, work, and energy. And so, as I mentioned, the origin of thermodynamics really is in the Industrial Revolution, where people were interested in converting heat to work, right? So think about steam engines. Okay, so we're going to be interested in, the development of machines that transfer heat to work and energy transfers, efficiency, and quality. Right? So we'll talk about the first law, which is essentially conversion of heat to work, you could think of, and second law is going to be related to efficiency. So thermodynamics, right, the name, thermodus, right, comes from Greek for heat, dynamiki, potential or power. So thermodynamics is the discipline that studies the relationship between heat and work. So in this course, right, our main focus is going to be on the first and second law, and we're going to be concerned with homogeneous closed systems, homogeneous open flow systems, and our applications are going to be limited to pure component systems. But we'll look at problems such as analysis of combustion engines, steam engines, heat pumps, refrigeration cycles, and steady flow devices. Okay, so first law, conversion of heat to work. Second law, efficiency. All right, all originating from the Industrial Revolution. All right, so in terms of supporting cast, So throughout the course, at some points, we'll try and mention some concepts from molecular thermodynamics. Now, this comes at a full disclaimer, right? So I am not a chemist. I do not expect you to be chemists, right? And, this isn't a class on molecular thermodynamics or chemistry or intermolecular interactions. The goal of this, though, is, as engineers, right, during early stage process conceptualization and design process, or during early stage process conceptualization and design, if you can shed any sort of insight in terms of what's happening in your system and why, it can really lead to significant advances in the design process. Right? So we'll talk about molecular concepts, okay? But I want to emphasize that this isn't a chemistry class, right? This isn't a class on intermolecular interactions. We want to think about molecules just so that we can try and gain some insight in terms of what's happening in our physical process so that we can become better design engineers. Okay? And, I am not an expert on this. You may find this awkward to think about it at first, right? But the hope is that if we keep trying to think and relate what's happening to molecules for certain occasions, it can help make us more proficient engineers. Okay. Additionally, in Chapter 2, we're going to spend a lot of time talking about phase diagrams and also working with equations of state, so analytic equations that we can use to perform real calculations as you would in the real world, beyond just working with tabulated data. All right, so intensive and extensive properties. So, the general idea I have in my head is how can I tell if I have an extensive property versus an intensive property? So if I have a homogeneous system, right? So homogeneous properties are uniform throughout. If I measure some property, such as density, and then I were to chop my system in half, so I could say cut my system in half, is that property the same in those two halves that I now have that I obtained by cutting my original system in half? And so if your property doesn't change, so if your property is insensitive to the size of the system, then it's going to be intensive. All right, so intensive properties are independent of the size of your system. An extensive property is dependent on the size of your system. So rather than density, if I were thinking about mass, right, or total volume, so I think about the total volume of my system. Now I cut that system in half, right? The volume of those two halves are going to be different than the volume of that system I started with. So an intensive property is independent of the size of my system, where extensive property is size dependent. Now, any extensive property you can make intensive by dividing by the mass or the moles in your system. Okay, so instead of total volume, I could calculate a specific volume, which would be the volume per mass. And if I were to cut that system in half, right, then the specific volume remains the same. Okay. All right, so as an example, all right, so we have a 250 milliliter beaker of water, and you've determined that the mass of water in that beaker is 250 grams. Right? Are these extensive or intensive properties? Well, if we go through our thought exercise, so we have 250 milliliters of water in a beaker, right, or equivalently 250 grams. If I were to, cut that beaker in half, right, exactly in half, what I would end up with is two beakers that are each now 125 milliliters each, or contain 125 grams of water each. All right, so total volume, the 250 milliliters, total mass, 250 grams, those are extensive properties. Okay, they're extensive. Right, we can make them intensive. Right, so what I could do is I could calculate the specific volume. So the specific volume is going to be the volume per mass, or in general, a specific property is going to be that extensive property on a per mass basis. So my specific volume, V, would be my total volume divided by mass, right? My 250 milliliters divided by my 250 grams, 1 milliliter per gram. Now, specific volume is intensive. If I were to cut that beaker in half, all right, the specific volume of water in those two halves would be the same. Now, you may not have seen something like specific volume before, right? So in this class, we'll use V a lot. Okay, you may be more familiar with density. Well, density is just 1 over V. All right, density would be grams per milliliter. All right, 1 gram per milliliter, the inverse. You can also think about the molar volume. Okay, so you're probably more familiar with mass-based quantities, right? In this course, we'll also use mole-based quantities extensively, right? So my molar volume would just be my volume per mole. Okay, and so how would I get that? Well, the conversion factor that I'll need is going to be my molecular weight or molar mass, and so the molar or molecular weight of water is 18 grams per mole. So that tells me that 1 mole of water has a mass of 18 grams. Okay, and so that's going to be unique, to given chemical species, but you can readily find it in the appendix of the book, as you'll see in the example problems that we'll work through. And so if I wanted to calculate the molar volume, so that's going to be my total volume per number of moles, well, I could get my number of moles from my mass via the molecular weight. So if I have 250 grams of water, and I know that the molecular weight of water is 18 grams per mole, so then in 250 grams, I have 13.89 moles. Right? So I could just as well convert the molar volume. Molar volume, just like specific volume, is intensive. If I were to cut that system in half, the molar volume would be exactly the same. And units, okay, so units are important. And so you should be comfortable with unit conversions, right? When we work through example problems, I'll try and take care and carefully go through problems and track units. To be perfectly honest with you, this isn't a course on unit conversions. They can be confusing, and so oftentimes when I solve a problem in later chapters, I will often just solve the problem in SI units, so I know that things will work out. But units are important to keep track of. You should be comfortable, performing unit conversions. And so you should have already had a class. So here at Miami, that'd be, say, CPB or MME 102. Should have heavily covered unit conversions. So they'll be emphasized in some of the examples in Chapter 1. And later on, you may find that I try and extensively use or exclusively use SI units to try and prevent this. There is an article posted on Canvas from CEP Chemical Engineering Progress, which details some examples just to emphasize how important it is to keep track of units. All right, so I mentioned that in this class we will talk about molecular thermodynamics. So again, my goal is this is not a course on intermolecular interactions. Okay, this is not a chemistry course. The goal of this conversation or discussion is that if we could have any sort of insight in terms of why are systems behaving the way that it is, it can make us better design engineers. Okay, so especially during early stage process conceptualization and design, any insight we can offer could lead to substantial improvements in design. Okay, so don't be intimidated when we talk about molecular thermodynamics, right? I want to emphasize this isn't a chemistry course. The goal here is to try and connect what's happening, if we can, into what's really occurring at the molecular level in our system so that we can ultimately become better design engineers. So as we talk about molecular thermodynamics, okay, the first thing we're going to talk about, or first thing we want to mention is what is an ideal gas? Well, in an ideal gas, the assumption is that molecules don't interact and they don't take up space. All right, so an ideal gas is a system in which molecules don't interact and they don't take up space. Okay, in real systems, molecules interact and molecules occupy space. Okay, so when we talk about molecular thermodynamics, right, again, our goal is to try and connect what's happening to the underlying intermolecular interactions so that we can become better design engineers. All right, so we said all molecules are going to interact. And so, it's been shown that, all molecules are going to interact, at least via dispersion interactions, so these induced dipole interactions, which scale as 1 over r to the 6, right, where this rij would correspond to the distance between my molecules, my pair interaction distance. Okay, so a common way to represent this is via Lennard-Jones potential, where this first term is just the second term squared, and accounts for the fact that molecules occupy space, right? So they can't be on top of each other. Right, and all I want to get at this, right, is if we say that molecules are interacting via dispersion interactions, okay, we have this potential model, we can get this simple picture. Okay, and all I want to get at, okay, is that if I'm in a liquid phase and I have molecules that are closely interacting, okay, on this potential energy diagram, right, this could be my pair interaction energy. So in a condensed phase, right, I'm in this region near the minimum in this potential. So in a liquid phase, I'm at this low energy region. If I'm in a vapor phase, right, so there's no such thing as absolute energy. We're defining zero as being an ideal gas, infinite separation. So in a condensed phase, I'm down here, right, this low interaction energy region. When my molecules are far apart, like in a vapor phase, okay, this is distance, then I'm over here. Okay, so the potential energy, or that pair interaction energy in a vapor phase, is higher, right, or is greater than that of my liquid, right? Or my liquid phase, when I'm here near the minimum, my pair interaction energy is lower than that of that vapor phase. Okay, what you see here is just that molecules occupy space, so they can't be on top of each other. You can only get them so close. Okay, but key takeaway from here is if I'm looking at this pair interaction plot, in a liquid I'm down here, in a vapor I'm up here. Okay, in a liquid I'm down here, a vapor I'm up here. My vapor is at a higher potential energy or interaction energy than in my liquid. Okay. All right. The last concept that is discussed in the chapter is this idea of my Maxwell-Boltzmann distribution. So Maxwell-Boltzmann distribution essentially just involves kinetic energy. So the idea is, what is temperature? Well, temperature is just a measure of the kinetic energy of the molecules in my system. Right? Molecules move except at 0 Kelvin. So kinetic energy is a function of temperature. Right? Temperature is a direct measure of the kinetic energy of my system. Okay, so the Maxwell-Boltzmann distribution assumes that the internal potential energy of the molecules in our system is independent of our kinetic energy. And so, here's an expression for the probability of observing a molecule with a given velocity in my system. And from that, the main key quantities that we'll use in our example problem is I can calculate the mean translational volume in my system. So this would be the mean translational velocity of a molecule in my system. Right? So the mean velocity of a molecule in my system, right, is going to be a function of t. So 8 kb, this is Boltzmann's constant, T is temperature, and mass is the mass of my molecule. So kinetic energy is only a function of T, as we'll see in our example. Velocity, though, is going to be dependent on both T and mass. Remember, kinetic energy is 1/2 mv squared. Okay. So velocity, right, is going to be a function of temperature and mass. This is the mean squared velocity. That's 3 kBt over m. Remember, kinetic energy is 1/2 mv squared, so the mass would cancel. So kinetic energy is only a function of temperature. Temperature is a direct measure of the kinetic energy of the molecules in my system. All right, so kinetic energy is only a function of T. Velocity is a function of T and mass. But if I have two phases in equilibrium, say water vapor and liquid water, they're at the same temperature, so the average velocity of the molecules in those two phases are exactly the same. All right? So, key takeaway here is molecules move except at 0 Kelvin. All right? The kinetic energy is only a function of temperature. And we'll work with a couple of examples with our Maxwell-Boltzmann distribution. Okay, and so here's just a plot. That probability distribution is a function of temperature. Okay, key takeaway is just as temperature increases, all right, the distribution becomes wider. Okay. All right, so just to give you, some sort of idea of, help build your confidence in your, molecular understanding, let's just look at a couple of examples to try and see what we're getting at with molecular thermo here. So evaporation of ammonia. A sample of liquid ammonia, NH3, is completely evaporated, changed to a gas, in a closed container. Which of the following diagrams best represents what you would see in the area of the magnified view of the vapor? Okay, so the idea is here in this first beaker. Okay, so I have a closed system, I have liquid ammonia, and I have a vacuum. Okay, so in my liquid phase, my molecules are going to be interacting closely with each other, right? I'm going to have molecules at a close interaction distance. Now, if I were to vaporize that, so now if I compare that to a vapor phase, so I'm assuming in that second beaker, now I have ammonia in a vapor phase, okay, in that same closed system. Well, in a vapor phase, right, I still have ammonia, it's just the molecules are now much further apart, right? So B is essentially that liquid that I started with. What I'm going to have in my vapor phase is A, right? I'm going to have my same ammonia molecules. It's just now those molecules are further apart. Right? So in a liquid phase, our molecules are close together. In a vapor phase, they're far apart. Okay, C, D, and E, all right, you can just get rid of those. They're ripping the molecules apart. We have no chemical reaction or anything of that nature happening. Okay, so liquid phase, molecules are close together. In vapor phase, they're much further apart. All right, so now let's look at boiling water. So we have a mole of liquid water that's in equilibrium with a mole of water vapor. Which phase has the higher internal energy? Well, if we go back, all right, so I'm going to go back a few slides. Okay, go back to this pair potential. Right? So the idea being, if I'm at a liquid phase, right, my molecules are at close interaction distances. I'm near this minimum in my potential. If I'm in a vapor phase, my molecules are further apart. Right, that pair interaction is going to be closer to zero. So now if I think about, so now I have a mole of liquid water that's in equilibrium with a mole of water vapor. Which phase has a higher internal energy? Well, just based on that pair interaction plot, I know that the potential energy or the pair interaction energy of my vapor phase is going to be greater than my liquid phase. So which phase has the higher internal energy? Well, that's going to be my vapor phase. Right? The vapor phase is going to have a higher internal energy than my liquid phase. Okay, cool. Okay, then to bring it full circle, so if you think in terms of the internal energy of vaporization, well, the internal energy of vaporization, which we could think of as being equivalent to the enthalpy of vaporization for now, which is something you may have seen previously in previous courses. But if I think about the internal energy of vaporization, right? So my vaporization process would be going from a liquid to a vapor phase, right? So it'd be the change in internal energy in going from a liquid to a vapor. Well, I know my vapor phase has a greater internal energy than my liquid. So if my process is going from liquid to vapor, then my change in internal energy would be the internal energy of my vapor minus the internal energy of my liquid. And that's going to have to be positive, since I said that my vapor phase has a greater internal energy than my liquid, right? And so, if you have a technician that's measuring, enthalpy of vaporization data for you or internal energy of vaporization, and they report back to you with a negative value, you could say, that's impossible, right? Rubbish, no way, right? Just by having some basic understanding of the underlying molecular level physics happening in your system. All right, heptane versus hexane. Okay, what is the main reason that N-heptane has a higher boiling point than N-hexane? Okay, so N-heptane, right, is alkane, so linear alkane containing 7 carbon atoms. Hexane has 6 carbon atoms. Right, so what this is trying to get at is heptane is harder to boil than hexane. Right, it's harder to boil heptane. So what that suggests to us is that we have, stronger interactions occurring in heptane as compared to hexane. Why? Because I have 7 carbons interacting with, each other as compared to 6. All right. So, the reason isn't that, heptane has a greater mass, right? It's that the heptane molecules attract each other more strongly. Why? Because I have 7 carbons in a heptane that can interact with 7 carbons in another heptane, where hexane only has 6. Okay. Last example, the pressure of an ideal gas in a fixed volume container is doubled without changing the number of moles of the gas. The average velocity of the gas will remain constant. Okay. remember that my velocity is only going to be a function of temperature. Okay, so our kinetic energy is only a function of temperature. Kinetic energy is 1/2 mv squared. So velocity is going to be related to temperature and mass. Okay, but since I'm keeping the well, hold on. I take it back, right? So I'm jumping ahead of myself. The pressure of an ideal gas in a fixed volume container is doubled. So pressure is doubled, volumes remain constant, and we're not changing the number of moles. So P is doubled, V is constant, N's constant, R is constant, so T is being doubled. Okay, so mass is remaining the same, T is being doubled, so my velocity, is going to increase. Okay, so I take that back. So in the last example, since P is being doubled and V is constant and N's constant, then T is also doubling. So as T increases, the velocity increases. Okay, there's our first set of notes. I'll see you in set 2. Okay, but again, I want to emphasize: don't be stressed out about molecular thermodynamics. It won't be, huge major component of the course. Right? My goal is just at certain points, it's advantageous to try and think about what's happening at a molecular level if we can, just so that we can try and become better design engineers. Right? This isn't a molecular thermodynamics course. This isn't a chemistry course. But I want to try and make you aware of some of those ideas for future applications and future use. Okay, we'll see you in set of notes 2.